public lecture series of TBAE. Professor Scott Hughes from MIT will give a very interesting lecture. Einstein's yes, the new astronomy of gravitational waves. Let us please thank this speaker.
Thank you. All right, so for the students who were here for my lectures today, there will be a little bit of repeat. This particular talk is going to go over a somewhat personal view of the entire development of gravitational wave astronomy as sort of, as I say, it's a bit of a personal view, so it's filtered through some of my own biases and my own experiences in this field, and conveys what I think, those of you who are students who are entering this field right now, you're amazingly lucky to be coming in at a time when there is so much opportunity to take advantage of this new instrument of discovery that has paid off so spectacularly over the past couple of years. So we heard, those of you students who are in the program here, we heard a little bit about what goes into these waveforms that are here. In some of the lectures tomorrow and on Wednesday, when Nurgis Mavavalu, who just walked in the room, begins to speak, we're telling you a little bit more about how these detectors work. What I want to do to begin is to give a little bit of the history of the development of this stuff. And when I really want to do in this field, this is about gravitational radiation, and it's useful to begin with the history of gravity itself. I actually like to begin with what I think of as the prehistory of gravity, which begins with how it is that we came to develop the understanding of gravity that prevailed for several centuries. And it began with humanity's beginning to study the movement of objects in the sky. So when we go back and we look at the historical record of this, at least the first documents that are written down in great detail come to us from the documents provided by Greek civilizations who tell us about the asteria and the planetes, objects which were fixed in the sky, the stars, and objects which wander, which we now call the planets. The first detailed written codification of this comes from Ptolemy's Almagest, which really said everything that we knew and for years stood as the dogma that at least in much of Europe, people were, in some sense, often by their churches, were required to adhere to. What this dogma told people was that the Earth was fixed at the center of the universe, and that these various fixed stars that were brought to us in this codification, they were pinpricks of light on a celestial sphere that surrounded everything. So then the question was, well, what's going on with these planetes? What are these wanderers that are present there? Well, they are taken to move on circular orbits on this circular sphere, on this giant sphere, that occasionally reverse direction. These were called epicycles. You look at the motion of a planet across the sky, and in order to make this the model, this is a model of the universe, to make the model fit the data, it was required that these planets would periodically stop what they're doing, go backwards, and then continue forward again. It's often the case these days in theoretical physics that when people want to criticize a model as a model gets more and more ornate, we like to say, you're just adding more and more epicycles. That can't be right. Epicycles are always wrong. But it's worth looking at the data. This is the position of Venus in the sky as observed over several months in the year 2004. And basically what these people did, the people who took this picture, they would point their camera at a particular point in the sky and take a picture every evening at where Venus was located. And look, Venus moves, then reverses direction. There's actually a gap in the data here because what happens is it passes behind the sun. Then it comes back out, and it comes out this way. We sneer at these epicycles, but that does a pretty good job of describing what's actually going on. Okay? And really, that's all you can ask of a physical model. Does it describe your data? And so we sneer at this now, but there's a reason this model held together for well over 1,000 years. It wasn't bad. Well, people began nonetheless thinking about whether you could make a model for the things we see in the sky that is perhaps a little bit simpler. And the first revolution was codified by Copernicus, who noted that you could achieve essentially the same motion in the sky of all of these objects if you demoted the Earth. Earth is no longer at the center of the universe in Copernicus's model, but it becomes just another planet going around the sun. People didn't like this. They liked the idea that the Earth was special. The Earth was the center of the universe. So this was met with some rather fierce resistance in certain quarters. But from the standpoint of science, it explained the data. And so it was plausible. Further progress, to refine this model even further, you needed new data. And not that long. So by the way, this was first published in 1543. There was a nova stella, a new star, appeared in the constellation Cassiopeia less than 30 years later. Now, in the Ptolemaic framework, the idea of a new star is a complete oxymoron. That shouldn't exist. The stars were eternal fixed points. You can't have something new. That's the opposite of what the stars are about. And so when I say pandemonium reigns, I'm perhaps exaggerating slightly in some ways, but not really. This was also happening at the time when much of Western Europe was going through the Protestant Reformation as well. And so lots of ideas were not being treated with great respect by those who disagreed with them. And so this just gave yet another thing by which people could disagree and essentially choose to kill each other over. And they did. Now, some people essentially just said, let's put all that aside and let's just gather data and see what the data teaches us. It's a philosophy of life that I think many of us hold near and dear to our hearts. And one of the most important in this epoch was Tycho Brahe, a rather eccentric Danish nobleman who had the fortune to be incredibly wealthy. So, being incredibly wealthy, he was able to buy an island off in the Baltic Sea and have privacy, put an observatory on this island, and not having a lot of other things that he needed to do with his life, basically devoted himself to cataloging the location of objects in the sky. So he precisely recorded the positions of all the stars that he could discern, and from night to night, he looked at positions of all the planets and very finely refined all of the data that had existed before this, and produced new data sets that eventually were taken up by his assistant, Johannes Kepler, who, especially after Brahe died, Brahe had his own theories of how to explain this, and Johannes would kind of go, and just sort of, say, just let me see the data. We'll talk about your model. After Brahe died, his analysis showed that all of the motion of those planets could be explained by three simple laws. The orbits are not circles, but they are ellipses with the sun at its focus. So in other words, if the star, our sun, is here, the planet might follow an orbit that looks like so. The planets move in such a way that it sweeps out equal area in equal time. So this means that if there's an imaginary string that connects the planet to the sun, then in an interval of time, let's say 1 month, it would sweep out this blue region here. Later in the orbit over here, it would sweep out this region here. The area of this blue region here is the same as the area of this blue region here. So that was something that he deduced from this data, that it moved around in this ellipse following this particular pattern. And he also showed that the square of the orbital period was proportional to the cube of the semi-major axis of that ellipse. So 3 remarkable quantitative deductions from this data set. And it's worth thinking about what really this has done. Okay, so the earlier models were kind of a hodgepodge of just empirical rules describing how each individual point tended to move across the sky. If you wanted to know about the orbit of Mercury, you went into Ptolemy's Almagest and you read about what the rules for Mercury were. If you wanted to know about the orbit of Mars, you went and you looked at what the rules for Mars were. If you wanted to know about the orbit of Jupiter, you had to look up the rules for Jupiter. What Kepler showed is that all of the planets obeyed the exact same rules, which are given by this. Massive simplification. Then it turned out that Isaac Newton was able to show that all 3 of these laws could be explained in the most simple way possible. If you require that 2 objects be attracted to one another by a force that is proportional to the product of their masses, inversely proportional to the distance squared between them, you reproduce all of Kepler's laws. So not only was there this, you didn't have to go and look up the individual rules for each planet, you had three simple laws that are themselves actually just consequences of one simple physical principle. It's important to note that this didn't just apply to planets. This is humanity's first quantitative and universal scientific theory. It not only described the orbits of planets around the sun, it describes the speed at which it describes the motion of objects falling near the Earth's surface. It described the orbit of the moon around the Earth. Shortly after this was formulated, the Galilean satellites were discovered, moons orbiting Jupiter. These rules described them as well. So we went from, in a space of about 150 years, we went from having these fairly random empirical laws that did a good job describing things, but were separate for each individual object, to a single universal quantitative description of what was happening here. Every single phenomenon involving masses being attracted to one another by what Newton called this law of gravity was accurately described. This was a phenomenon, and it really had a tremendous amount to do with essentially kicking off the scientific revolution that began about 400 years ago. It was celebrated by many people, and I like to quote a poem that was written by Alexander Pope, who said, "Nature in nature's laws lay hidden night. God said, let Newton be, and all was light." This is how people really regarded this. But there was a rejoinder that came along. It did not last. The devil howling, "Ho, let Einstein be," restored the status quo. So what's going on with this? Well, Newton's laws were amazing. They described almost everything, but there was one annoying problem that emerged over centuries of observation, which was that Mercury's orbit didn't quite work. Now, to give a little bit of background about this, if you have a single planet orbiting the sun, it moves, according to Newton's laws, in a closed ellipse. Our solar system does not consist of a single planet. Okay? It's the sun plus, depending on what year you define a planet in, 8 or 9 additional planets that orbit around it. And it always will be. That's why I say both, for people like you, Badri. If you include the impact of all of these other planets, that ellipse precesses. So what that means is that the arc of the ellipse is constantly advancing. So it sort of looks like this on one orbit, then like this, and like this, da-da. So it's not an ellipse that closes. The influence of the other planets causes this ellipse. The angle at which this ellipse sort of points to the distant stars changes with time. This has been known for a long time, and it became a project of mathematicians and what were called natural philosophers in the 19th century to calculate the rate at which this happened. And this was an extremely difficult project. This is actually where the field of perturbation theory, for the students, the physicists in the room, this is where it was really invented, was in order to study this problem, because you were considering the small perturbations of all the other planets on the orbit of Mercury. And with a lot of work, people were able to show that this ellipse should advance by 5,556 arc seconds per century. Now, it's useful to have a little bit of intuition as to what that actually means. So you can convert an arc second into a degree. There are 3,600 arc seconds in 1 degree. I have a way I prefer to describe it. If you turn and you look at that clock, and you ask yourself, how much angle does the minute hand move in 15 seconds? In 15 seconds, the minute hand moves 5,400 arc seconds. So this extra angle per century is roughly the angle swept out by the minute hand of a clock in 15 seconds. Now, when this was measured, it was found to be 5,599 arc seconds per century. So there's a discrepancy of 43 arc seconds. Put it again into these terms. Let's look at that clock again. 43 arc seconds is the distance that the hour hand moves in 1.5 seconds. So I'm a theorist. And when I see numbers like that, I think to myself, come on, measurement error. Can't be that big a deal. But no, in fact, astronomical objects can be measured with such precision that an angular discrepancy accumulating over a century, that's equivalent to the distance the clock's hour hand sweeps through in 1.5 seconds, stands out like a sore thumb among all the measurements. So this was real. And it confused the heck out of people for quite a long time. So as people were trying to understand what to do about this, our friend Einstein was busy working in his patent office, reformulating the foundations of physics. For our story, the impact on his reformulation on gravity is the thing which is important to us. So two of the impacts that Einstein's theory of relativity has on gravity are important for this story. First, the famous one, as I like to say, this is the one equation that when I'm having a conversation with my mom, I'm allowed to use. E equals mc squared tells us that all forms of mass and energy are equivalent, which for our story, this means that all forms of energy gravitate just like masses gravitate in Newton's gravity. And the second one that's important for us is the idea that the speed of light is a universal limit. No information can travel faster than that speed. So what are the consequences of this? Let's begin by thinking about the impact of E equals mc squared in gravity. All forms of energy respond to gravity. Light is a form of energy. Therefore, light must experience gravity. And indeed, there's a prediction of this, which is the gravitational redshift. As light climbs against gravity, it loses energy and colors shift to red. I am using a green laser pointer here. So I put it on my hand and I see a nice green spot. Put it on the ceiling and it's a slightly redder spot. Now, of course, you seeing it can't tell that because the light goes up, it reflects, and then you undo the redshift. As it falls, the reflected light gets the redshift taken away. But if someone brought in a ladder and climbed up here and looked at that, you would be able to see that it is slightly redder than it is down here at the base. Granted, you would need very precise measuring equipment to do so. Doing it with your eyeball probably wouldn't work. So if that doesn't convince you, it's worth noting that this fact is used every moment of every day, probably by you. Because this is worked into the global positioning system, which is used in many mapping apps on your cell phones. The satellites that form the basis of the global positioning system aren't just, a couple meters above my head. They're several thousand meters above your head. Excuse me, several thousand kilometers above your head. Several hundred at least. And the gravitational redshift associated with signals going from your cell phone to the satellites and back is significant. And the timing delay that is introduced because of this redshift is a significant effect. If you did not account for the gravitational redshift effect, that essentially means clocks work at a different rate in orbit than they do on the surface here, GPS accuracy would degrade by 8 meters per minute. So in the space of about 30 seconds, everything would sort of move to the other side of the room, according to your GPS maps, and a little bit later in the day, it would just be completely off. Now, one of the first things that Einstein did when formulating his theory of relativity was he knew about this issue with Mercury. And so he developed field equations, he figured out how to solve these things, and so he says, let's look at what the orbit of an object is when I include physics beyond Newton in here. And so, he sits down, you crank through a little bit of math, and he indeed found that an orbit is not a closed ellipse, but that the orbit of the angle associated with that ellipse increases slightly with time. And this is actually a homework assignment that I give to my students in my general relativity classes to work out this formula. What's cool is it's simply expressed in terms of numbers that you can go off and look up. You need to know the mass of the sun. You need to know the semi-major axis of Mercury's orbit. You can find that on the internet. You need to know the eccentricity of Mercury's orbit. You need to know the period of its orbit. You can put all those things are quantities that you can look up, and then you can just plug it in this formula and see what the number is. In many ways, if you think about when Einstein did this calculation, which is around 1915, actually getting the numbers out was probably the hardest step, okay? Because nowadays, we just plug it into Mathematica and we evaluate the formula or put it on a calculator. He actually had to do some arithmetic, which for many of us is now the hardest part of math. You plug them in there, and it turns out to be exactly the historical discrepancy. When this result came out, Einstein wrote in a letter to his friend Paul Ehrenfest, "I was beside myself with ecstasy for days." Now, slightly personal, when I first read this note, when I first read this quote, I think I was supposed to think to myself, wow, what an amazing achievement, what a monument to how deeply dedicated to the science Einstein was. But I have to admit that when I first read this, my reaction was, what a nerd. But I have to confess, I'm going to show you guys some results a little bit later, after which, when I first saw it, I was beside myself with ecstasy for days. All right, so the other bit of information that relativity provides, the other important element, is that no information can travel faster than light. So the students who are here saw me use this slide earlier today. If I have two objects that are widely separated from one another, and one of them moves, according to Newton, the red star will immediately know about the yellow star's new position. That can't be right. There has to be some kind of a mechanism to transmit in the gravitational interaction the new position from one object to the other. That mechanism is in fact widely known in other fields of physics. So the same shortcoming applies to electromagnetic interaction, which had been studied in detail for decades prior to Einstein's formulation of gravity. So if I have an electric charge, if it's just sitting at rest, it radiates electric field lines that come out of it in all directions in a perfectly symmetric fashion. But I make it move, I accelerate it, and there develops a kink in the field lines. And this kink propagates outward at the speed of light. I paused it right here. You can sort of see at large radius, it doesn't yet know about the charge's new position. At small radius, it does. And the little transition region here that connects where it does not yet know about, it has not yet received the news that a charge has moved, and the bit that has received the news, this kink in the field propagates outward and communicates the news of the charge's new position. And that kink is indeed nothing more than radiation. This is exactly how light is produced. So all the photons by which we are seeing my talk coming out of my laser pointer, they ultimately originate in electric charges undergoing an acceleration like this. Now the same thing has to happen in gravity. And in this case, the kink that communicates the news that the field has changed, that the sources have moved to a new position, they propagate outward at the speed of light, and they manifest themselves as a gravitational tide. So around here, I'm showing you a ring of test masses, so little objects that on their own would just be sitting, not doing anything. A gravitational wave comes along, this radiation that comes from my accelerating masses, and it squeezes and stretches them, just as the tide of the moon squeezes and stretches the Earth. Okay, so if you imagine that this was happening with a period of twice a day, this would be exactly what the geoid of the Earth, the surface of the Earth, looks like as a function of time. The oceans are particularly susceptible to this, so they tend to bulge. In a given location, they will tend to bulge and then go back in. The atmosphere follows that. But what we're going to be looking for is a more subtle phenomenon that looks just like this kind of a tide. It sort of stretches along one axis, squeezes along the other, and does so in an oscillatory fashion, bouncing back and forth from stretch to squeeze to stretch to squeeze. So it's a really simple task to measure these things. You just need to set up some masses that look like this and look for oscillations in the distance between them. Okay? You know, go home, set up some masses in your backyard. You've made yourself a gravitational wave detector. Now, unfortunately, when you then estimate how much of a stretch and squeeze you expect, you can see I've exaggerated it somewhat here. For a realistic, the kind of source that we actually expect nature would provide that would produce these things, we expect the shift here to actually be equivalent to about 1/1000th the radius of an atomic nucleus for every kilometer of separation. In other words, if this were 1 kilometer, then the amplitude of this little oscillation would be 1/1000th the size of the nucleus of an atom. Atoms are small, nuclei are significantly smaller. 1/1000th of a nucleus is pretty small. So this is the point at which most people would do the calculation and then go, all right, that was an interesting idea, let's do something else. Well, people didn't give up on this. And the first thing you might think to yourself is, can I find some other way in which this radiation might make itself apparent? And indeed, Just as light carries away energy from a source, my laser is slowly draining power from my battery, the lights that are powering our room, they're coming from a power plant somewhere. All forms of radiation carry energy. Gravitational waves must carry energy. So if I imagine that I have two dense stars that are orbiting each other, and this produces gravitational waves, well, then the waves will carry away energy from this source. That leads to the expectation that the system must be losing energy to that radiation, and so the stars must fall together. So if I watch a binary like this, over time, I expect to see the stars getting closer and closer and closer. We just have to hope nature provides a system that does this. Turns out, in 1974, exactly such a system was discovered. So we got lucky. There was a serendipitous event. We found two neutron stars, the cores of normal stars, roughly 1.5 times the mass of the sun, crammed into a ball about 12 or so kilometers across, orbiting another object that was almost exactly the same. We are particularly lucky in that one of the objects in this binary is a pulsar. So a pulsar is a spinning neutron star that emits very regular pulses. They are so regular that many pulsars actually are better timekeepers than the best atomic clocks that humanity has produced. Okay, they are not all of them are that good, but all of them are quite good. And so because we essentially now have a clock in a very interesting orbit, that gives us a means to map the properties of this orbit with very high precision. So this thing has been watched since 1974. And what has been discovered, so for the students in the room, Badri Krishnan showed, I think, exactly this plot a little earlier today. It was shown that the orbital period is actually slowly decreasing with time. It's worth looking at the unit. So the units here, I've unfortunately covered it up. This is the change in the orbital period in seconds as a function of the year in which the observations are made. So you can sort of see over 25 years, the orbital period got roughly 30 seconds shorter. Okay? And there's additional data that goes beyond this now, so it's probably now more like 45 seconds shorter. Very small effect, but because it's such a good clock, we can measure it with amazing precision. And a point here, which I believe Badri made, but I want to emphasize it again. Every one of these points, the error bars here have actually been, the error bars on the measurement of the period have been amplified by about a factor of 100 so that you can actually see them. Okay? You can barely see them, and that's even after we've multiplied the error bars in the period by about a factor of 100. And so what is done is you make measurements at a particular orbit, you learn about the properties of that orbit, and then you make a prediction for how the orbit will evolve in time. The result is this blue curve. It's worth emphasizing that blue curve is not a fit. They really just use data at an early time to predict what it should be at all future times, and it passes directly through this thing, even taking into account the fact that these error bars have been amplified by about a factor of 100. This was justly awarded the Nobel Prize in 1993. You know, for the longest time, this was the most, this and the other binary star systems that have been discovered that are also inspiraling due to the gravitational wave emission stood as really the exemplars of general relativity and gravitational wave emission for quite a long time. But people didn't give up on this idea that maybe we could measure this radiation directly. In particular, this rather ornery character, who Nergis is going to probably tell you more about in her lecture, he really could not let go of the idea that perhaps you could make an instrument that could make a measurement of this distance that was a fraction of the size of an atomic nucleus. So in 1972, Ray Weiss, he wrote a paper that examined how well this can be done using the technique of laser interferometry. And he concluded that if you used powerful lasers that exquisitely controlled all the noise in the experiment, and we're going to talk about, for the students, we're going to talk about this a lot more in some of the upcoming lectures, it could be done. It certainly could not be done in the 1970s, though. But it was enough to convince people that this was not crazy. It was really, 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 really hard, but it was not crazy. Well, it might have been crazy, but it wasn't impossible. Yeah, I think I'll go with that. It was borderline crazy, but not impossible. So let's talk about the basic idea here. So what Weiss showed is that if you take very pure laser light and you set it into perpendicular arms, and bounce it off of distant mirrors, the light will recombine in such a way that the intensity that comes out of this beam splitter depends on the position of these mirrors. So let's look at this interference pattern a little bit more carefully. So light is a wave. And when light comes back together in here, you design it such that the instrument usually operates with there being no signal coming out of this thing. As the mirrors move back and forth, you break that delicate interference pattern, and the oscillations in the intensity there, at least in principle, encode the signal that you want to measure. Now, Nergis is sneering a little bit because the way the experiment is actually done is a little bit more complicated than this, and I believe she will talk about some of the details a little bit more, but this, in a nutshell, is the key idea behind it. You're looking at very carefully monitoring the positions of these mirrors by the way that the interference pattern is read out when the light is recombined here. And the most important thing is that by doing this very precisely, you can measure shifts in the positions of those mirrors that's actually trillions of times smaller than the light's wavelength. That trillions of times smaller is absolutely necessary because even though light has a fairly short wavelength, but it's still a lot larger than the nucleus of an atom. Okay? So you need to get down by a factor of about 1 trillion in order to read this thing out. And Weiss showed that this was possible. Difficult, but possible. Over the course of the next 20 or so years, and I'm going to leave some of the details of some of that development to future lectures, within the United States, 2 facilities were built to make measurements of these things to implement Weiss's ideas. One of them is in Hanford, Washington. It consists of the mirrors in these things, or as I mentioned earlier in one of my lectures today, these are separated by about 4 kilometers. These are also separated by about 4 kilometers here, the site in Livingston, Louisiana. These are actually sensitive to gravitational waves that oscillate in a frequency band that very entertainingly corresponds almost exactly to what the human ear can hear. Now, it should be emphasized, we can't hear gravitational waves directly, but it's an interesting way to think about the signals that they carry. We can compute them, we can measure them, and we can turn them into an encoding that our ear can hear. And when we do this, the signal that is read directly out of the detectors goes right over to what the human ear is sensitive to. There's another detector that is running in Europe, in Pisa, Italy. It's quite similar to LIGO in its initial design setup. This needs to be updated. I just realized this is from an older version of this talk. It's actually been operating at fairly high sensitivity now for closer to 2 years. And it has been contributing quite a bit to the observing runs that the LIGO detectors are making. So, whoops, hang on a second. There it is. Bit of an error there. Along with building these detectors, it turns out to be important to understand how to produce gravitational waves. Understanding them is going to be useful, should we ever measure these things, as we thought 25 years ago, to taking the data and learning about the sources that produce the radiation. And so I had to show a picture. This is my PhD supervisor, roughly what he looked like when I met him, who played a large role in initiating a major research program to understand the waves and their sources. So he was the mentor and organizer of many groups, largely in the United States, but also in Australia, India, and Europe, mentoring many of the people and bringing them together to begin thinking about how to understand gravitational wave sources, and how to measure them and how to learn about these sources from the measurements. One of the things that came out of these analyses, so it turns out the sources that make the strongest gravitational waves are objects that are very massive and move very rapidly. So you need to take a lot of mass and compress it into a very small volume. And some of the best sources of all are things involving black holes. So nothing is more massive or more compact. And so we expected sources that involve black holes to be some of the very strongest gravitational wave sources. A lot of my astronomy friends, when I was working on things related to binary black hole sources as sources of gravitational waves, would always sort of tell me, well, that's a really plausible case, but nature doesn't produce 2 black holes that orbit each other. We don't have any evidence for that. And you could say, well, of course you don't have any evidence for that. They're black, they're dark, you can't see them in your telescopes. They'd say, yeah, but still, nature probably doesn't produce those kinds of things. So this ended up, the argument would say, well, you're probably only going to be able to see them or hear them using gravitational waves. And they'd say, okay, fine. So that's where we were for a while. So for the longest time, it was essentially theorists doing calculations and our experimenter friends building these instruments and making them work. So for those of you who are in my lectures today, this will be a little bit of a repeat of some stuff I did earlier. What we learned by this research program that Thorne and others initiated is that the gravitational waves richly encode very useful astronomical information about the properties of the sources that generate them. So here is an example of a gravitational waveform. And the students who are in my lecture today know that I like to take signals like this and then turn them into sounds so that we can all hear what gravitational waves would sound like if our ears were sensitive to them. So what you heard in that little sweeping chirp was the members of the binary losing energy as gravitational waves carried them away, and then they fell towards each other. When they fell towards each other, they went a little bit faster. That made them radiate a little bit more strongly, which made them fall towards each other even more, which made them go a little faster, which made them radiate a little bit more strongly, which caused them to fall in a little bit faster. You had this sort of runaway process that just went faster and faster and faster. So in a signal like that, if we're able to measure this, the analyses showed us that we'd be able to learn a lot of information about the masses of the objects that made up the binary that produced these gravitational waves. Here's another example of one. Now in this case, what I've done is I've made the two objects that are in this binary spin very rapidly. When I turn this into a sound, let me turn the volume up a tiny bit, make sure we can hear this structure. So that additional that's on top of that, that is due to the sort of unique and fascinating way that spinning objects behave, the way that spinning objects gravitate in general relativity. Remember, E equals mc squared. All forms of energy are equivalent to mass in a relativity theory. And so all forms of mass gravitate. And so the energy bound up in an object's spin gravitates. But what general relativity teaches us is that it does so in a different way. Right now, everyone in this room is being drawn towards my powerful gravitational attraction. Okay? You're able to resist it. But if I were to spin enough, okay, the kinetic energy associated with my spin, assuming I don't get sick, the kinetic energy associated with my spin actually makes my gravitational attraction somewhat stronger. But it does so in a way that's a little bit weird. You would be pulled towards me a little bit more, but you would also tend to be dragged around into co-rotation around me. So, you know, by doing this, if I spun quickly enough, you would all essentially be involuntarily forced to dance in this crazy space-time whirl that I would set up around myself. Well, that crazy space-time whirl leads to these additional modulations on the signal here, and also lead to this oscillation on top of the chirp. But from the standpoint of an experiment, this is a very unique signature to go after. If we can measure signals that have that additional structure on top of it, it's a smoking gun of the fact that we've got very interesting spin structure associated with these things, and that's rich with the kind of astronomical information we would like to learn about these things. One last example. If I have black holes that are very massive, the only thing, all of the frequencies associated with the source actually tend to move to low frequencies as the black holes get bigger. Think of an analogy with a bell. If you have a little tiny bell and you ring it, it's a very high-pitched ring. Ding, 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 ding. Medium-sized bell might be more like ding, 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 ding. And then you make a really massive bell and it kind of goes bong, bong. Black holes are the same way. Really small ones have high-pitched rings. Really big ones have low-pitched rings. And so if I have really big ones, I'm only going to catch sort of the last couple cycles that come at the end of this. They have a mathematical form that looks just like the ringing of a bell. But it's a bell that decays away very, very quickly. And so it's almost more like just a popping noise. It sounds kind of like a bubble popping.
Can I ask one question?
Yes?
The last part of that.
Yeah.
Is that exponential?
the one I played previously, it actually terminates in something that looks like this. And so yes, it terminates in exactly something like that. But in those cases, that structure was, because it's happening at higher frequencies, it decays in the same number of oscillations, but it's at higher frequencies. So, you know, this structure is compressed to a bit where it basically can barely be discerned, okay? If you had more precise equipment or really good ears, perhaps you could. So this was the story. Essentially, this is where the field was for much of my professional life as a professor at MIT. Myself and my theoretical colleagues were busy making waveforms, thinking about what we could learn from these things. Professor Malvavala there in the back and many of her friends at the building on the other side of campus were busy making all these detectors work. And everyone was sort of assuming it was going to work someday. So the thing actually began a run officially the day after September 14th. It was supposed to begin, I believe, on September 15th. But, you know, nothing special was going on with it, so it was basically just on and running. I believe Ray Weiss actually wanted to shut it down because he was concerned about some weird noise source, and then people basically said, nah, Ray, just let it run. Which turned out to be a good thing. Because on this day, for the most part, you were just seeing the normal behavior of output that just indicates nothing but noise going on. And then all of a sudden, boom, this appeared in the two detectors in Hanford, Washington, and Livingston, Louisiana. People have taken this actual data that was measured here and also encoded it as sounds. There's your noise. Let's play that again. You can hear the little boop right there. It bears a pretty stunning resemblance to the little ring down pop that I played for you about 2 slides before. And that's because this is indeed, as we're going to see in a moment, this was nothing more than the last couple cycles, much like that thing that I played for you before. It's a couple little cycles of that inspiral, plunging, coming together, and getting the last little bit of ringing that happened from this. I told you guys that when I read Einstein's quote about how he was beside myself with ecstasy for days, I kind of was like, nerd. When I first was given a briefing, now I'm not a member of the LIGO collaboration. I've always managed to keep myself sort of sneakily on the outside, which has allowed me to review certain papers and to serve on certain review committees over the years, which has probably proved useful for the collaboration. But it means that I was not officially allowed to know about all of this stuff. But a few friends, there were a few professional reasons for this, decided to sneak me a peek of what this looked like. And I must tell you that the day one of my friends, he was describing this to me, and I started asking questions, and he said, "This was all right. Here, let's just say it's this." And he pulled out his phone, and he held it out, and he showed me one of these traces. He kept talking. I have no idea what he said. I was just lost in that image for a little while. I began thinking about black holes as gravitational wave sources in 1993. So this was, in one instant, 22 years of my career, suddenly changing from fiction to reality. As I've told people, there are 3 moments in my life which, when I think about them, I can still feel the emotions that I felt at that moment. I think about the image that comes to my mind. I think of when I see my daughter's face for the very first time when she was born. I see my father's face for the very last time when he was terminally ill. And this data. It had that much of an impact on me. Because it was clear, it changed everything. And frankly, it was a moment of also, all hyperbole aside, suddenly I was like, thank God it wasn't a waste of my life. So that's my own personal take on this. Now, over the next couple of weeks, while people, as Badri described in his talk, they spent a lot of time convincing themselves that this was real. And then once they were convinced of this, they also began diving in and analyzing what produced this signal. And it became clear that this could only be produced by 2 black holes, exactly as Badri described in his presentation earlier today. And the best waveform that fit this corresponded to a black hole of 29 solar masses merging with one of 36 solar masses, leaving behind a black hole of 62 solar masses. I mentioned a few moments ago that arithmetic is not my strong suit. But I do know that 29 plus 36 does not equal 62. In the course of doing this, 3 solar masses vanished. This happened over a space of about 0.2 seconds. You convert, basically 3 solar masses were converted into gravitational energy and radiated away from the system. If this had been light, this would have shined as brightly for those 0.2 seconds as 175 billion Milky Way galaxies. This was, for that moment, the most luminous object in the sky. But it was luminous in gravity. And so rather than seeing the bright light of 175 billion Milky Way galaxies, the test masses of the LIGO detectors went like this by about 0.1 atomic nuclei. Now, many of our friends were justly honored by this. So this is Ray Weiss when he first began conceiving of all this, and then just after receiving his Nobel Prize from the King of Sweden. Kip Thorne, when I first met him, looks a little bit different these days, also receiving his Nobel Prize, and then sharing it there with Barry Barish, who was instrumental in making LIGO move from conception to reality. We had a big party, and there's Nergis and I and our friend Matt Evans celebrating the moment that the news came through, when at about 6 a.m. we were all over in the LIGO labs waiting for the news to come through. Now, since then, we are just finding more and more pairs of merging black holes. So these are all the ones that have been published since that first one. As you can see, this is 1, 2, 3, 4, 5, 6, 7. OK, so there's 9 here. I have not shown the initial. Is that right? Do I have 9? Yeah. So there's 9 in there. When the detectors are working well, we are now, the LIGO detectors, I say we, but it's really the collaboration of very hardworking people putting this all together. Several binary black hole mergers every month are coming through. I mentioned during one of Badri's talks today that you can all go to the, if you have a smartphone, you can get an app that allows you to follow along with this. And there have been 3 alerts sent out, so likely detections, although many of these then go away under further analysis, but there have been 3 since the beginning of July. I was giving a public talk to a group of high school students about 4 weeks ago, and it went off while I was giving my talk. And when it does that, the phone actually makes a chirp noise. So thank you, LIGO. That was good timing. As I just said, so there have been 3 since July 1st. Yeah?
What's that thing on the right top?
This one?
No, the blue thing before the chirp.
Oh, this? Noise. And I'm sure that someone who actually was deeper into the analysis can give you a bit of a more technical explanation of what exactly the noise actually is. But the thing to note is that it's excluded by some of the filters in this thing. I mean, these, the detectors bop around. Nergis, you want to comment on that?
Another thing is you notice it's only on the blue curve.
That's right.
It's on a single detector noise. If it's a gravitational wave, it should show up in multiple detectors. So that's excluded just by that alone.
Yep. Yeah, so that's a very important sanity check. If it were real, not only would it be in both detectors, but it would be offset slightly in time, because the signal has to travel through spatial distance from one to the other, unless the orientation is precisely lined up.
The same thing also 17 with the next one there.
Oh yeah, over here. Yep. Yeah. What's fascinating about this is it's a little bit hard to see the axes here. The vertical axis shows masses. These are the masses of black holes that we know about. So this is 1 solar mass, 2 solar masses, 10 solar masses, 20, 40, and 80. The purple dots are all the black holes whose masses are close to those of stars that were known and characterized basically by traditional astronomical methods, largely using X-ray telescopes. These blue ones are all the ones that gravitational wave detectors have found so far. And notice, there is a definite offset in the mass distribution. So not only, despite which so many astronomers told me, as I was a young and impressionable graduate student, not only do black holes form binaries and merge, but the ones that do that are very different from the black holes that had been characterized by most telescopes in the past. We are still really astronomers, and some of my colleagues, people at the postdoc in particular who I work with at MIT, we're still trying to understand what it is that is the mechanism that produces these and why they are so different from those that are seen in by other methods. But that's not just all. So a particularly exciting one is that in August of 2017, detectors picked up a very long signal. This thing lasted for about a minute. That told us that we were seeing the inspiral of two relatively low mass objects. The more massive they are, the stronger the waves they produce, and the more quickly they sweep together. If it's spiraling through slowly, they must be relatively low mass things. 2 seconds after the signal ended, some space-based observatories detected the flash of gamma rays in the sky. Putting together all the information, so this was picked up by the LIGO detectors. There was a non-detection in the Virgo instrument, but the fact that it didn't see it was actually a very interesting non-detection, because it actually told us that this source was in a handful of sort of regions in the sky where Virgo had no sensitivity at that moment. These detectors are more sensitive to some parts of the sky than to others. And so people were able to very rapidly zero in, and they found a galaxy. This is what the galaxy looked like in archival data from about 10 years ago. And on the next day, August 18th, suddenly it had a companion. That companion ended up becoming the most intensely studied object in the sky. There are many papers that were written on this thing. On at least one of them, I believe someone figured out that 20% of the professional astronomers on Earth are co-authors on that paper. And Nergis can tell you that writing this thing was a very pleasant exercise. It made everyone really friendly and get along great, right? Anyhow, it's a bit of a sociological challenge getting everyone to work together well, but they did it. It was quickly determined that this arose from two neutron stars that were in orbit about each other that collided and produced a gamma ray burst, a tremendous explosion. This has revolutionized many things in astronomy and astrophysics. This has had consequences for cosmology. This ended up providing us with a new way of determining large distances. Something that's near to my heart because I helped to develop some of those ideas. By studying the light curve that was produced by the fireball that was left behind, people have learned that this is probably one of the most important mechanisms for stars producing elements heavier than iron. So if any of you has any gold jewelry, chances are that the gold atoms in your rings or your earrings or your necklaces, they were actually forged in a binary neutron star collision billions of years ago before our solar system condensed. So what is the future of this? Well, these are the instruments that are making these measurements now, LIGO and Virgo. GEO is essentially a test instrument in Germany that is a place that is really used to develop some of the advanced measurement techniques. TAMA is a similar one in Japan that is a forerunner to a detector that is going in to a mine in Japan called Kagra. LIGO is helping to build an instrument that will be located in India. It had been hoped for a while, and this is an old slide, so I had to unfortunately X this out. It had been hoped for a while that there would also be a detector in Western Australia. The funding hasn't come through for that, so I've had to X that one out. But we expect in the future, so LIGO and Virgo will probably be joined by Kagra in the next several years, and hopefully LIGO India not too far after that. Moving farther into the future, the European Space Agency, in concert with the American NASA and several of us in this field, we are developing plans to put a gravitational wave detector that would fly in space. The benefit of going into space is that you become sensitive to much lower frequency gravitational waves. Earth is a noisy place at low frequencies. If you try to detect if you want to detect bigger black holes, you need to be sensitive to lower frequency gravitational waves, and you just cannot do that on the Earth's surface. But if you go into space, you can. In particular, this would allow us to listen to various processes that involve the kinds of massive black holes we see in the cores of essentially every galaxy that we look at. I am personally spending a lot of my research time these days focusing on one of the what I consider to be one of the most interesting sources for LISA. Those of you who are students in the summer program here will hear more about this in my 4th lecture tomorrow. But for now, I'll just say that there are some sources that involve essentially small objects. By small object, I mean sort of 30 solar masses, going into a very complicated strong field orbit of the big black hole that lives at the core of a galaxy. this ends up producing really complicated orbits. I will show you some examples of this in just a moment, which then leads to very ornate gravitational waves that are rich with information about the properties of the big black hole and about the space-time structure that surrounds it. Developing these things is looking like it is going to be a many-year process of getting it together. So I've been working on modeling efforts for these things now for probably the past 10 or 15 years, and there's quite a large community that's doing this. And it's really important that we involve students in this work when they are young. So I've discovered that my daughter has an intrinsic talent at modeling these sources. Okay, so I was sort of amazed at how well this actually corresponds to the real thing here. I think she has some small errors in modeling some of the conservative corrections to the interaction, but it's close. It's really close. And so I think with a couple more decades of training, she'll be in good shape. And that'll be probably just an about right time for this thing to fly. Now, taking the models that we have so far, let me play you one example of the kind of signal that we hope to hear from this. So what I'm going to show you, turn the volume down a little bit here, is the orbit of a small body orbiting a big black hole, and you'll see the gravitational wave that is produced from this thing. Now, I should emphasize that the actual signal that is produced from this thing is at frequencies way below what the human ear can hear, and it also lasts for about 6 months. That's probably a little much to ask you guys to wait through. So I've sped the whole thing up, which both made it last for a reasonable frame of time and means that you can hear the signal. So let's let this thing go. So this is the example of that very complicated orbit that is produced from this thing. Over time, you start to see some patterns emerging. And this traces back to a question that a student asked me during one of today's lectures. So let me just pause this for one moment. No, go back. So let's let this pause for just a moment here. All right, I'm just going to let it go. So what you're seeing in this is that the signal is loudest when the small body passes close to the big black hole. And then there's a moment where it's quiet while it moves further away. And that's simply because when it's passing close, it's moving fastest. Moving fast gives you stronger acceleration, stronger gravitational wave emission. But you'll start to see with time that the contrast between the quiet and the loud pieces is getting smaller. That's because the orbit is becoming more circular with time. You're bleeding away that eccentricity, and it's becoming more and more circular as it falls deeper into the strong field. This is a rapidly rotating black hole, so there's an additional modulation, because this orbit is being whipped around by the space-time dance of this thing's spin. It goes higher and higher and higher. And then it just abruptly cuts off as the small body falls into the black hole. This is the kind of signal that many of us are gearing up, and it's something I'm personally excited about. We've actually discovered that in this complicated pattern, there are surprising regularities that emerge. And one of the things that my colleagues and I are now working on is trying to see whether we can exploit some of these underlying regularities. Instead of imagining that we've got one very complicated signal here, it may be more fruitful to think of it as the simultaneous sum of 100 or so simple signals. So we're looking at that right now to see whether that gives us any fruitfulness to do it. Fortunately, we have about 15 years before Lisa launches to get this working, and then my daughter can finish off the job and we'll be done. All right, I'm going to end there. So the thing which I hope has been communicated to you, what I think is particularly wonderful about this, people have described what LIGO has achieved, what LIGO and Virgo has achieved as being equivalent to when Galileo first looked at the moons of Jupiter and opened up this new thing that this new world beyond our atmosphere. Personally, I think it's even deeper than that, because we are probing the universe now using a sense that we did not even have before. I'd say this is more akin to when the first hominid crawled out of the cave, looked up at the sky, and thought, what's that? And that's where we are right now. So I like to say our ears are open. Thank you.
Questions, please.
Yes.
Do we need to measure something
For Lisa, do we need another?
Black hole around a supermassive black hole to detect some gravitation. Maybe?
So to go to lower frequencies, so to go to look at things that involve like massive black holes, yes. So we need to develop, I mean, we cannot do that with the instruments that currently exist on the surface of the Earth because they are not sensitive. It's like the analogy in astronomy is it's the difference between using an optical telescope. At higher frequencies, you have X-rays and gamma rays. At lower frequencies, you have radio and infrared. Gravitational radiation also has multiple bands like that, and you do not use, in the same way that you don't use an optical telescope to look at an X-ray source, you wouldn't use a ground-based high-frequency detector to look at a supermassive black hole. And you have to go into space to make those measurements.
But since these supermassive black holes are expected to be very old, doesn't it also require that another black hole have already been
I'm not understanding one word you're saying there. Another what? Oh, black hole. Another black hole. Yeah, that's right. That's right.
Should have already been swept by the.
Yes. Yes. So in my lecture, so when I'm talking about, so I didn't talk too much about the astrophysics of these sources. I will a little bit more in my lecture on tomorrow's second lecture for the students who will be here. But for these kind of ones, the one where I just played you this video, the thing to remember is that the black hole in the center of a galaxy, so I have a black hole down here at the center of a galaxy. This is about 1 million solar masses. It's embedded in a star cluster, which has many tens of millions of stars in it. These stars have complicated orbits that interact with one another in a very complicated way. The most massive members of those stars will actually quickly evolve to form black holes. And so it's actually expected, and people have done the direct detection has so far been a little elusive, but there's some tentative evidence that there could be, as sort of a subpopulation of the star cluster, something like 20,000, well, let's say 2,000 to 20,000 smaller black holes. So there's sort of a cloud of black holes expected to be near these things. Yeah. So I believe that the constraint I remember seeing is that people think that the total mass in that cloud is on the order of 20 to 50,000 solar masses worth. And there's some evidence from observations that were done using the New Star telescope that people have begun to detect some of these black holes. So these guys, they're sort of the remnants of the many millions of stars that are here. These things will interact with one another, and it's very rare. We sort of expect about once every 100,000 years, there will be an event in which multiple black holes interact with each other and then go on to an orbit that looks something like this. Okay? Now, per galaxy, it's rare. But the number that LISA will be sensitive to, you only need, if it's 1 every 100,000 years, you actually then expect that LISA will measure about 100 of those events per year. Now, some of the other sources that LISA looks at are actually a black hole like this orbiting another black hole like this. That actually is very well understood astrophysics that people are doing a lot of work on right now. They form when galaxies collide with each other. And that happens all the time. Not in our local universe, but in the earlier epochs, so billions of years ago, sort of to those of you who know cosmology, sort of redshifts of 3 and 4 and 10, in that kind of regime, black holes forming binaries after the collisions of their host galaxies are expected to be actually very common. And so that's another important source for the space-based detectors, is essentially 2 million-ish solar mass black holes orbiting. And what's wonderful is that general relativity has no built-in notion of a scale to it. So the waveform that LIGO uses to measure 2 30 solar mass black holes also exactly describes the waveform that LISA will use to measure 2 3 million solar mass black holes. It translates exactly. Turns out that you measure the one with a lot more precision. And so the point that Badri made is that we need to improve our models in order to really measure that thing well. But that's a challenge I think many of us are eager to make.
So can I follow up on the to the binary? Or
It's-
PGR?
No, it's the number of cycles plus the amplitude. So it's just higher, it's both higher signal to noise ratio and number of cycles. Yeah.
I have one question again.
Yes.
Briefly. I mean, when we have a charge moving, it creates electromagnetic field where electric and magnetic fields create each other and
Yes.
they go into whatever they like.
Right.
I mean, is there an analog for gravitational waves? I mean, what are
There is.
magnetic and electric?
So remember that this the tensor of space-time, it's a quantity that has multiple components associated with it. And so in essence, it's gravitational waves come in two different polarizations. It's the two polarizations trading back and forth with each other that helps to source this thing and produce the wave that propagates across the universe. Now, we don't measure one of those propagations in those polarizations in certain directions. Okay, and fundamentally, it's actually the curvature that is doing this. But that's an object with multiple components associated with it. And so what's happening is the wave is propagating. You know, in a relativity point of view, we don't like to think of the electric and magnetic fields as separate objects. They are just different representations of components of a different underlying structure, the Faraday tensor. And so in that language, when the wave propagates, it's just different components of this tensor converting from one to the other. The exact same thing happens in general relativity when I have a gravitational wave propagating. It's just different components of the mathematical objects that describe gravity converting from one component to the other as it propagates along.
But you also use the term gravitomagnetic.
Yeah.
Something.
That's right.
What is gravity, and then what is gravitomagnetic?
So what I meant by that, I was actually in that case referring, so those don't refer to radiation. So I'll use an example that I sort of whimsically used a few moments ago. So like I said, you all are now drawn towards me because of my intense gravitational attraction, right? That I would say is gravitoelectric because it basically behaves just like the electric field of a point charge, okay? I'm just standing here, my mass attracts your mass, and that's all there is to it. Now if I start spinning, I am generating a new component to gravitation that's associated with the currents of my masses moving around and around. And that, as we described in some of our conversations earlier today, sets up a new aspect to what gravity can do that actually causes things to sort of want to whirl around me. I would call that gravitomagnetic because the way in which that aspect of gravity behaves is much more similar to what a magnetic field does. Does that help?
Yeah.
Okay.
But also, the existence of gravitons, that's so equivalent of photons, is it somehow related to all these, and does all these say anything about gravitons?
So gravitation, the detection of gravitational waves, let me use an analogy. Water waves, okay? That is the propagation of a wave in a fluid. Would you quantize a water wave? You wouldn't, right? Because you know that water is itself essentially the fluid is kind of an approximation that emerges after you average over the properties, the collective properties of many, many molecules of water. Now, are these just a superposition of gravitons, or are they some kind of an emergent phenomena that comes from some deeper underlying molecule of space-time? I have no idea. And I think anyone who claims to have a really good idea is probably deluding themselves at this point. You know, this is really stepping into ground where, you know, how many angels can dance on a head of a pin, right? We just don't have a really good experimental guidance there. Yes?
The gravitational wave patterns you showed, the published ones.
Yeah.
So what is the timeline, GPS timeline for those patterns?
You mean from detector to detector?
No, the ones that you showed, yeah, these ones.
Yeah.
What is the GPS time length for the...
Oh, so how long did each of these events last? Yes. It varies. So let's see. So the ones that I know, where's my pointer? So this one I know lasted a little more than a second. That one I know fairly well because I was the referee for the paper on that one, so I had to learn that one very carefully. This one's probably a little bit more like half a second. Some of these, this one was probably about 0.1 seconds. You know, it varies, and the duration of them directly tells us about the mass of the objects that are involved. So Badri gave a little calculation today where he sort of showed you how you can plot the frequency as a function of time, put it on the right power law, and you get a line. And from that line, the slope of the line tells you about the Chirp mass of the system. So every one of these are on the order of at most a second or two, and in many cases a fraction of a second. This particular one, which I have not shown you the gravitational wave for, okay, it is about 3,000 oscillations, and it actually lasts something like 80 seconds. Okay, and that's because these are much lower mass objects. Nope, I think we do.
After one gravitational wave detection, a gamma ray burst is detected. And
yes.
There's a 2 seconds delay between them.
Yes.
If one of them are coming with speed of light, what is the reason of that delay?
So we don't fully understand the mechanisms by which gamma rays are actually produced in these things. But there's no reason to expect them to occur exactly one after the other. So the way, our best understanding of what the gamma rays come from is, so these two stars smacked into each other. They began to do something very violent that we don't fully understand. Part of that is that there was then a jet of material that was emitted from whatever remnant was there. That jet actually slammed into, so we'd like to talk about the vacuum of space, but space actually contains a fairly low density cloud of neutral material. The gamma rays actually came from that jet slamming into the material in what we call the intergalactic medium. And so it took time for the jet to form, for it to launch out, to hit the intergalactic medium, and to produce the shock waves that lead to those gamma rays. Indeed, it took about 2 seconds from what this data told us. So we don't necessarily expect them to be exact, right? So, and that is, as I say, I'd say the main takeaway from this is that the mechanism by which the gamma rays are produced, it's independent from the mechanism by which the gravitational waves are produced. And so there is, different things that are happening, and certain processes needed to evolve for a little while before the gamma rays were produced.
So there's one more confound in this, which is for this particular object, GW17, LIGO and Virgo didn't actually see the merger.
Right.
The merger occurred at a frequency which was already in our noise. So we also, that gap, it could also be that the merger occurred within those 2 seconds at some point. So we didn't see it. So that's the other confound to that. But detecting more of such systems should, with higher sensitivity at these higher frequencies where the merger is taking place, should answer exactly the questions that Scott is bringing up.
Yeah. Yeah, this is why everything at the end of the day, one of the reasons I wanted to start and go back to the prehistory is to emphasize how much our understanding is driven by new data. And at the end of the day, that's what needs to be the thing that drives all this.
School time.
All right, thank you.